So, before today, we could have actually done this first problem using the rules that we already have. What we would have to do this problem using the rules that we already know is we would have had to have converted it by actually multiplying this out. So x cubed times 4 is 4x cubed. 7 times 4 is 28. X cubed times negative x squared would be negative x to the 5th. And 4 times x cubed would be, oh, we already did that one, sorry. And 7 times negative x squared is negative 7x squared. And then we would have put it in, just for clean algebra's sake, we would have put it in descending order. And then we would have taken the derivative of each term. 5 times negative 1 is negative 5. X to the 5 minus 1 is 4. 3 times 4 is 12. X to the 2nd. 2 times negative 7 is negative 14. X to the 1st. And the derivative of 28x is 0. So we could have done this problem, if we had fairly decent algebra skills, without needing a product rule. However, the product rule makes our life a whole lot easier. So here's what we're going to do. This rule says that if your function is in fact a product of two different functions, u of x and v of x, what you do is you take the derivative, and let's make sure these are different, you take the derivative of u of x and give it as a partner to v of x. And then you take the derivative of v of x and give it as a partner to u of x. And then you multiply it out and you add those together. So applying that logic, we'll work first with what's in the first set of parentheses. And that's x cubed plus 7. The derivative of x cubed plus 7 is 3x squared. Agree? Okay. Then we will work with 4 minus x squared. And the derivative of 4 minus x squared is negative 2x. Okay? And then what the product rule says that we do is we take the first part of the product, which is x cubed plus 7, and we multiply it by the derivative of the other part of the product. That's negative 2x. And then we take the second part of the product, 4 minus x squared, and we multiply that by the derivative of x cubed plus 7. And then we add those together. So then y prime becomes negative 2x times x cubed minus 2 times 7 is negative 14x, plus 3x squared times 4 is 12x squared. 3x squared times x squared is 3x to the fourth, and that's a subtraction. And then if we rearrange this and clean it up a little bit, we'll notice that we have 2x to the fourth terms. And those 2x to the fourth terms combine to be y prime equals negative 5 x to the fourth plus 2x squared, I'm sorry, plus 12x squared, misspoke, minus 14x. Which is the same thing we would have gotten if we had multiplied out the original function and differentiated term by term. Now, is one better than the other? No. Is one shorter than the other? No. Not for this problem. But you can see where this could get pretty ugly too. Okay? Those could have 4 or 5 terms each. Or it could be something besides polynomial functions, which we'll get into later. We could have logarithmic functions. We can have exponential functions. Yes, I saw Shannon going, oh, please don't talk about those. Actually, exponential and logarithmic functions in calculus are easier to find derivatives of than it was to learn how to do simplification back in finite. So it won't be as bad as what you might think it might be. So, product rule. The way that I write it is not the same as the way that they're writing it at the top of this page. This is my version of the product rule. If your y, your function, is a product of two other functions, then the derivative of y is g f prime plus f g prime. Just using the prime notation for the derivatives. Okay? Take the derivative of both parts, both factors, swap the derivatives, and add everything up. If we have a product rule, we also have a quotient rule. This is the quotient rule. The quotient rule is similar to the product rule with two small changes. You still take the derivative of the numerator, you take the derivative of the denominator, and you swap them with each other. But you don't add, you subtract. Okay? Multiplication, division, opposite operations. Add if it's multiplication, subtract if it's division. And then you'll divide the whole thing by whatever the denominator was to start with, but square it. Now I could prove to you why this works. That's a big long proof. Takes about a page and a half, but I could verify for you that it always works. But I'm going to assume that y'all would rather take it on faith rather than me having to explain to you why it works. Just that this is how it works. So we need to know how, not why. So taking the same approach as we did with the other one, I'm going to color code because I think it actually makes it easier to figure these out if you color code things. So I'm going to get all my colors over here. And as you're learning how to do this, you might want to try this too, because this actually does help a lot of people get things associated until they kind of get the process in mind, and then after that they don't need to do it anymore. So we're going to have a numerator, which is this part. And I'm going to go ahead and take its derivative. And its derivative is 3. We have a denominator part also, and its derivative is negative 2. So this is what the rule says that we do. To find f prime of x, we take the numerator times the derivative of the denominator, and the denominator times the derivative of the numerator. And then we also take the denominator and we square it for the new denominator. So the part that I just put in purple there, the plus sign, the bar and the fraction and the squared, is actually part of the rule. Okay? So one more time. Numerator times derivative of the denominator. Not plus, minus. I'm sorry, that's my bad. Minus, because we are subtracting. Denominator times derivative of the numerator. All over denominator squared. Now there's a little rhyme that goes with this that helped some students learn it. It's called high d low minus low d high over low squared. Okay? With this being the high and this being the low, and the d meaning derivative. So if that helps you remember it, it's high d low minus low d high over high squared. But once you get to this part, and I want to see this step, I don't care what else you do after that, I want to see that step, because this tells me you knew what you were doing. Anything that comes after that might have an arithmetic mistake in it, or an oh shoot mistake, okay? So I don't want, everything else is fine, but I want to see that step. So this simplifies or cleans up to be f prime of x equals negative 2 times 3 is negative 6x, negative 2 times 2 is negative 4, minus 3 times 5 is 15, and 3 times negative 2x is negative 6x, but we're subtracting it, so we're going to say plus 6x, over, and you don't have to multiply out the denominator unless I'm given a really good reason to. I actually prefer not to, because it's easier to put in the calculator if I don't multiply it out. Now I do notice up here in the numerator that I have some things that'll cancel. 6x and 6x will cancel out, and 4 and negative 5, negative 15 becomes negative 19 over 5 minus 2x in parentheses squared. And those are all perfectly good answers. And believe it or not, my labs usually will accept the first one without needing to do any further simplification. It takes a lot more typing. This is what it's looking for, but it realizes that this is equivalent to that. It might fuss and say, the answer that you have entered is equivalent to the correct answer, but it'll usually take it. Yes?
So I'm confused. I got 19 over, I think it's negative, and that's because in the rule it says take the denominator multiplied by the prime of the numerator.
Mm-hmm.
So, but you took the numerator and multiplied it by the prime of the denominator first, and then it switched.
Oh, yes. Thank you so much. Yes, yes, yes. Let's start over. I know exactly what I did, and I wasn't thinking when I did that, so thank you for catching that. Yes, addition is commutative, subtraction is not. So let's start back here. go at this again. And let me rewrite the rule up here in my version of it. F prime of x is going to be denominator times derivative of the numerator minus numerator times derivative of the denominator. And all that's going to happen is there's going to be some signs change. And then it's over the denominator squared. So here's what I should have done. Sorry, folks. I promise I'll go back and get some more coffee. We start off with the denominator, which in our case is 5 minus 2x. Multiply it by the derivative of the numerator, which we know is 3. Minus the numerator, which we know is 3x minus 2, or plus 2. Times derivative of the denominator, which we know is negative 2. And we did have the denominator right, or I have the denominator right. 5 minus 2x, quantity squared. So 3 times 5 is indeed 15 minus 6x minus 3x times negative 2 is negative 6x, but there's a negative in front of it, so that's actually going to be plus 6x. And 2 times negative 2 is going to be negative 4, and minus negative 4 is going to be plus 4. And again, I'm not going to bother that at all. I'm going to leave that alone. So what changes is really the sign in the numerator because of my swapping the terms around. Negative 6x and 6x will still cancel out, but I have 15 plus 4 rather than these being subtracted. They're now going to be adding. So 15 plus 4 is 19 over 5 minus 2x squared. So it will not be negative 19, it will be positive 19. And it's because this term should have been first and that term should have been last.
So we did mistake and listed denominator first.
Yes, you always list denominator first. So it's, and I think I said the rhyme wrong, it's low D high minus high D low over low squared. And thank you for catching that. Bonus points for you today. Let's try a second one. Let's make sure I don't mess the second one up. So I've got a numerator and a denominator. Here's my numerator. Its derivative is 2. Here's my denominator. Its derivative is 4. And my rule says I take the denominator, the low, d high, the derivative of the numerator. So that's 2. And I'm going to subtract the numerator times derivative of the denominator. And then put that whole thing over the denominator squared. And again, the denominator is 4x plus 3. And then any cleanup you do after that is kind of up to you, because we have dy dx right here. So dy dx, or y prime, or f prime of x, is equal to 8x plus 6 minus 8x plus 4 over 4x plus 3 squared. And 8x, again, don't get used to this, it doesn't always happen, but 8x does cancel 8x, and 6 plus 4 is 10. Now, you want to practice with those. And even as I said, when we have things that are not polynomial factors or not polynomial numerators and denominators, we still use this rule. And we will apply that because a great many times your cost function will be either a product or a quotient of two things. So if the total cost to manufacture X items is given by C of X, the cost function, and the average cost per item is C average X, meaning C of X over X, then the marginal cost is the derivative of C of X over X, which is C prime of X, C prime average, okay? Now be careful with the notation and the language here. Your marginal cost function is the derivative of your average cost. That's very important. It's the derivative of the average cost function, not the cost function. Because we're talking about marginal average cost, not marginal cost, okay? So suppose the cost in dollars of manufacturing X hundred small motors is given by this function as long as X is between 10 and 200. Find the average cost per 100 motors. Okay, the average cost is C of X over X. Cost per motor. So since we have a function for average cost, we're going to divide this function by X. I'm not going to write it this way because you'll more easily understand the next step if I write it this way. So that's actually divided by X. Now I could have drawn a line and put the whole thing over X, but that just looks like a three-story fraction and gets confusing. So if we divide things by X, what do we usually do when we divide by something and we're working with fractions? If I have, if I have 1/2 divided by 2/3, what do I do with the 2/3? I can't think in words either, so. If I were going to do this problem, what would I do with 2/3? Flip it and then multiply, okay? The math word is take the reciprocal and multiply, but flip it, okay? We'll flip it. 1/2 times 3/2, okay? That's how we would do that. Okay, we're going to do this the same way. We're dividing by X. Imagine if that X were over a 1. We're going to flip it and then multiply. And after you see what happens and you realize it's always going to happen this way, then you'll be able to take a shortcut to get your answer. But when I flip that, remember it's the second one I flip, not the first one. This is going to be times X over 1. So when I flip that, I'm actually going to multiply this whole numerator by X, and I'm not going to do anything to the denominator. So I'm really going to multiply the numerator by X and get 3X cubed plus 120X. So this is my average cost function. It's C of X over X, but this is algebraically simplified because I don't have a way to deal with 3x squared plus 120 over 2x plus 1, all divided by X.
Because you have X to begin with, and it's X over 1, the reciprocal should be 1 over X, is that right? Okay.
I think I need to go back. Sorry. I think I need to go back and start over today. This is just not my good day. Yes, Shannon, thank you. I said take the reciprocal, and then I didn't do it. So, 3x squared plus 120 over 2x plus 1 times x is going to be 2x squared plus x. And if you haven't, as of this moment, learned that it's okay to call the teacher out when you think she's wrong, please write that lesson down. Especially when it's this teacher in the afternoon and hasn't had that second cup of coffee yet. I don't mind a bit. So are we all good on this now? We got me straightened out. Okay, this is the average cost. Okay. Find the marginal. The word marginal should always tell you to find the derivative. Because marginal is always a rate of change. So since I'm going to find the marginal cost function, and I have a quotient, then I will need to use the quotient rule to find my marginal cost function. So C prime average, because remember you're doing the derivative of the average cost. So average prime of x is going to be the derivative of this function, that function, it's the same function. And the way that we do it is we take the denominator, 2x squared plus x, multiply by the derivative of the numerator, which would be 6x, then subtract the numerator, multiplied by the derivative of the denominator, which is going to be 4x. And then we're going to take the existing denominator and square it. Now that actually is just fine for the answer.
Isn't that 4x plus 1?
Does it convert to 1?
Yes, it does. Yes, this derivative is 4x plus 1, and this one is just 6x. Now, as long as you're sure that you've gotten your derivatives taken correctly and you've applied your quotient rules correctly, at this point, honestly, I would stop. I would not necessarily try to multiply that out. Yes, it does involve more typing in the answer box, but it works. And what they're actually going to do in reality is what they're about to ask us to do here. It says, as we shall see in the next chapter, average cost is generally minimized when the marginal average cost is 0. Find the level of production that minimizes marginal average cost. Okay, in other words, we're going to take, and we're going to try to find where the average marginal cost, C prime average of x, is equal to 0. How's the easiest way to do that? There's two, depending on what your likes and dislikes are. One way is algebraically. And I will kind of rearrange this a little bit to make it easier to actually plug things in. I'll put the 6x in front, 2x squared plus x minus 4x plus 1 times 3x squared plus 120 over 2x squared plus x squared. And I want to know, where is that equal to 0? And the only way this is going to be equal to 0 is if the numerator is equal to 0. And at this point, if I'm gonna solve this algebraically, I'm gonna have to simplify the numerator at least. I don't have to do anything about that denominator, but at this point, I would have to simplify the numerator to find where it's equal to 0. So 6x times 2x squared is 12x cubed plus 6x squared. Minus 4 times 3 is minus 12x cubed. Minus 4 times 120 is minus 480x, and 1 times 3x is 3x squared, and 1 times 120 is 120, and I would set that all equal to 0. So let's see, I've got 12x squared minus 12x squared. Good, that disappeared. Or 12x cubed, I'm sorry, 12x cubed minus 12x cubed.
Move it over just a little bit, please.
So then looking at what we've got left, 6x squared plus 3x squared, 9x squared, minus 480x, plus 120. So I need to solve that equation. Does everybody just love factoring? Not me. I factor when I have to. I don't like factoring ugly things like that. I might be able to make it look nicer by factoring out a greatest common factor, but it's still ugly. I don't like factoring ugly things. They make this handy dandy little thing called a quadratic formula. Remember that? Minus b plus or minus the square root of b squared minus 4a over 4ac over 2a. And all you're doing is plugging in, this is a, this is b, and this is c. It's just arithmetic. So x equals, the opposite of b is 480. Plus or minus, 480 squared. I need a calculator. $230,400 minus 4 times a is 4 times 9 is 36 times c, which is 120, is 4,320. So I'm going to go ahead and take square root of what's under the square root sign. 230,400 minus 4,320 is 226,080, and I need to take the square root of that. And I get about $475,000. Or about 475, not thousand, I'm sorry, 475. So 480 plus or minus 475. And if you want to call that 0.50, that's fine, but you know, we're talking in dollars here, and this is average. And we're going to divide by 2 times a, which is 36. I'm sorry, 18. 2 times 8. 2 times 9 is 18. So 480 minus 475 divided by 18 says that would happen at about 0.28. Now going back up here and looking at it in terms of, what does that mean? Well, that's going to be about 0.28 items. If you had to round 0.28 items, which way would you round it? So at one item, marginal cost might be 0. Okay. You're really likely to only make one. No. What are you more likely to make? 480 plus 475. So about 53 or 54 items. So your marginal average cost is 0 when you're making the first item or when you're making the 54th one. Make sense? I said there's 2 ways to do it. Did we have to do it algebraically? No. Let's go back and let's actually try to graph our function. And actually, we don't even need to graph the whole thing. Since algebraically we know that this is equal to 0 only if the numerator is equal to 0, we can graph the numerator and find out where it's equal to 0. And we don't even have to simplify it to do that. And hopefully it'll tell us that we were right. See if I can do this so we can have things kind of where we can see them together. So 6x plus times 2x squared plus x minus 4x plus 1 times 3x squared plus 120. And we know that that's equal to 0 if we let one of the lines be the y. If y equals 0, that's the x-axis, so it's basically going to be at the y-intercepts, right? I'm sorry, at the x-intercepts. It's going to be at the x-intercepts because y equals 0 is the equation of the x-axis. So we're looking for x-intercepts. So since I have a ballpark answer already, we'll try to set this up to where we can see what we're doing. So we'll go from 0 to, let's say, 60. And I have no idea what y needs to look like, so I'm going to do zoom 0 and let it fit y however it sees fit. Let's see what we find. Okay, apparently we're not finding anything because it's staying on negative y. We need y to be positive at least a little bit. Oh, I did that backwards. No, apparently the graph is never positive. That doesn't make any sense. It has to be. Let's see if my lack of caffeine is the issue here. I may have messed up the algebra. So let me double check. Oh, I did not put the answer in the PowerPoint. I will look and see if I made a mistake, and I will get back to you, because I think I may have made a mistake either here or in the way that I put it in. So I'll go back and look, because I know the procedure more or less was right, but I could have made a mistake. We've already established I made two. So, anybody got any comments or questions? No? So we will come back to that one. Make me a note to check that one. Because the last thing we want to do today in the remaining time we've got, and this is not going to be the only class period that we spend on this, is we're going to talk about the chain rule. It has been my experience that the chain rule is tricky at first because you have a hard time figuring out what the inside and the outside are. Because chain rule refers to what's inside a function and what the outside function is. So what we're talking about here is composition of functions. Okay? So let's talk a little bit about this and get us going first about composition of functions. You have values of x that can be plugged into a function that give you values of y that are called functions of x. Y and f of x are the same thing. You can take the result of plugging y into that function f and plug it into a new function g, and you have something called the composition of g of f of x. Now, in order to kind of make that make a little bit more sense, and it doesn't go along necessarily with this, I want to go with something a little simpler first. Let's pick a couple of fairly simple functions and play around with composition of functions. So f of x is going to be x squared. G of x is going to be the square root of x. And h of x is going to be 1 over x. There's three different functions. None of them are real hard. One's just your basic squaring function, one's your square rooting function, and one's taking the reciprocal function. Okay, basically it's just taking the reciprocal of whatever x is. If I ask you what is f of g of x, what does that tell me I need to do with g of x? What does F's rule say to do with whatever you throw in it? Square it. So take g of x, there's g of x, and do what F says to do to it. And F says square it. Okay? Now we can simplify that. I'm not saying we can't, but that's not what the goal is here. What's the inside function? What got dropped in? G of x. What's the outside function? What's g of x wearing around it? F of x. So this is the inside function. This is the outside function. Okay? Don't try to overthink it. Yes?
Can you show us how it works? Like, how would that be written as like the G-O-F?
And I think that's confusing notation, but that's a good question. The other way to write this is f of g of x. And you read that little zero as of. It's not a multiplication sign, okay? It's called a composition sign. I hate this notation because it's easily confused with another different algebra operation that symbol means. I like this notation because this tells me what I'm supposed to do with that. I'm supposed to put that in place of x, okay? So this and this are the same thing, but this is more instructive, especially for what we're trying to learn from this, okay? Let's try again, try a different one. What if I ask you what is h of f of x? What does that tell me I'm supposed to do? F of x is x squared and h of x is 1 over x. What does that look like? 1 over x squared. Now in this case, it doesn't look as easy to tell me what's the inside and what's the outside, does it? But what if I remember that this is also written as x to the negative 1? So then another way to write h of f of x is x squared to the negative 1 power. And that does simplify to x to the negative 2 power, which is identically the same as this. So it didn't lose meaning. It has the same meaning. But can you see now what's the inside and what's the outside? Yeah. Here's your inside. And there's your outside. One more. What if I ask you what is g of f of x? What does that look like? What's g do? It takes the square root of whatever you put in it. So in this case, g is the outside function. And we would be able to deal with it better if we looked at it as being like that, but those are the same thing, right? And the inside in both cases is x squared. Now granted, these both simplify to x, which means we're not really going to do a chain rule with something like that anyway. We'll just, simplify it and go on. But it's easier to identify in and out. And that's the goal of this next section, is to be able to identify inside function and outside function. So that's why I wanted to start this, even though we may not finish it today. So now let's talk about chain rule, now that we know what we're talking about when we say inside function and outside function. F and G are functions, the composite function of f and g is either g of f of x, or it can be f of g of x, depending on which one's the inside, which one's the outside. The only things you have to remember, it has to be all of the domain of f if f is the inside function. We have to consider any place that f wouldn't exist. Okay, for example, we were calling if we were calling h 1 over x, h isn't defined at x equals 0, so we wouldn't be able to use 0 in the domain of g either. So we call this g of f of x because f of x is the input and g is what tells us how to come up with the output. So these are examples of composite functions, and so since we're talking about inside and outside, Matt Delosier wants to see you. I forgot to bring you the email. Vice President for Student Affairs asked me to send you to his office. And I have no idea what it is. It's in the classroom building. Do you know where the security office is? Okay, go straight down the hall and it's on the left right past security. Just check in with him and find out what he needs. Okay, what would the outside function here be? Because we obviously have a composed function. So what's the outside function here? Raised to the fourth power. That's your outside. And then the inside is what's inside the parentheses. This can be rewritten to the 1/2 power. What's the outside function? Yeah, it's the 1/2 power or the square root. This is the inside. Keep in mind, we're not doing any calculus yet, but it'll be easier to do the calculus if you can determine what's inside and what's outside, okay? This is actually a product function. So this one's kind of messed up in a way, because it's actually the product of two functions. It's the product of 5x squared, and the other factor is a chain rule problem. This is not chain rule, unless you would want to consider x as the inside, but we have a rule that handles it without chain rule, so we're not going to try to fool with that. But here we have an inside and outside function. The outside function is the 4th power. And what's inside is x cubed plus the square root of x. Now, when you read the book, it is not going to refer to inside and outside functions. That's me. That's the way I figured out how to explain it in a logical, non-math manner. I can tell what's inside something, what's outside something. It wants to talk about u's and f of u's and all that kind of stuff. And I'm not going to go into that notation, but I will tell you how to make this make sense. The chain rule says that if you're going to take a derivative, what you do is you take the derivative. Don't worry about what that says. I'm going to tell you what it says in English. In order to take the derivative of a chain rule problem, and this is a chain rule problem because you've got an inside and an outside function, and that's what makes it chain. You take the derivative of the outside, keep what's inside, and link it, there's where the chain comes in, to the derivative of the inside. Okay? So what this is telling you to do is that if you have this situation where this is your function, the way you take the derivative of that function is you take the derivative of the outside times the derivative of the inside. And I just use the prime notation because y'all know what that means. It means take the derivative, okay? So here's how we do this problem. First, we determine what's the outside. What's the outside function? It's when I raise it to the negative 2 power. So my outside function is here. And the derivative of something raised to the negative 2 power, you bring the power down in front. What do I do to the power after I bring it in front? Subtract 1 from it. Did anything in here change because of what I just did with the power rule? No. So this is my inside function, what was inside the parentheses to start with. Okay? Now, got one more step. Then I also link out, this is where the chain comes in, and take the derivative of what's inside. Okay? Take the derivative of the outside, then take the derivative of the inside. We're done. There's nothing more to do. And that's equal to y prime or dy over dx. Do you need to multiply out and finish and clean that up? Really not much of a way to do it anyway, it's just kind of ugly. Yeah, I know your algebra teacher told you never to use negative powers. They weren't just fine. Your calculator knows what a negative power is. It knows what to do with it. Okay?
So
That's it. That's it. I don't even want you to try to clean these up. I just seem to leave them the way they are. Because I can see what you're doing here. If you go moving things around, I may lose track of what you were trying to do.
Don't mind, I have last one, get away with it.
Yep. If you don't, let me know. But we got away with it all last year and it worked fine. The only time it won't is when it says, no, that's not correct. Okay, that means whatever you did here, you messed up somewhere in the calculus part of it. Okay?
Is there a vote on this?
Yeah. So we've got about 15 minutes. Might be able to do more than one. Let's go to the top of the next page. Find the derivative of y equals x squared times the quantity 5x minus 1 cubed. And remember, all of it doesn't have to be chain rule. This one is not necessarily just chain rule. This is also a product. Okay? So what we're going to do first is we're going to take the derivatives of both pieces. The derivative of x squared is 2x. The derivative of 5x minus 1 raised to the third power is chain rule. And the chain rule says take the derivative of the outside, which is the third power, which will be 3 times the parentheses, and drop the power to 2. Put the 5x minus 1 back in the parentheses, and then take its derivative, which is 5. Okay? And then the product rule says take the first times derivative of the second plus the second times the derivative of the first. Take both derivatives and then swap them. Always take your derivatives first. That way, if you need to apply a chain rule, you can apply it when you're taking the derivatives to start with. Now, does that clean up? Yes. Do you have to clean it up? No. Nothing wrong with it the way it is. Yeah, I guess we probably do need to do that. There we go. The only thing I probably do need to do here is I need to close that outside set of parentheses, because this closes these and that closes that one, so I do need one big set. Now, if you want to clean it up, yes, you can. If you wanted to clean this up and find y prime in a nicer form, 5 times 3 is 15, times x squared is 15x squared, times 5x minus 1 squared, plus 2x times 5x minus 1 cubed. Now that's as far as I would go. That's as far as I would ever go myself, and I'm not, like I said, I'd be probably happy if I just went that far. The reason I'm saying probably don't try to clean it up, and I'm just going to give you a word of warning, if you go through and ask to help me solve this, what my math lab does, and this hurts me no end, is they say, oh, you have a common factor of 5x minus 1 squared. Factor that out. Now, I don't think that looks a bit better than what it looked like up there, but they do. So if they do that to you, that's what they did. They looked and said, oh, there's a common factor, factor it out. And I think they might have even went ahead and multiplied that out, but I don't think you need to do that.
Why does x or 2x drop down to become x squared?
It didn't. It didn't. That x squared is this one.
So
It's the first,
it's not the derivative.
no,
Okay.
it's the first factor times the derivative of the second factor,
Okay.
plus the second factor times the derivative of the first factor. It's two rules combined. It's a product rule, but in order to do the derivative of your second factor, that's a chain rule. So that's what you're going to find is that all the rules work all the time. The problem is sometimes you have to apply more than one rule to finish the problem. Now, does anybody have any questions on this one? I don't think we want to get into applications today. I just wanted you to see a couple of chain rule problems and some product rule problems and practice. Go ahead and practice. Now, in a couple of minutes that we've got left, I have news for you. You have Thursday off. You're the only one of my classes that does. Everybody else, I'm making them come and take a quiz. I'm going to let you have the day off. I'm going to be in Asheville, North Carolina on Wednesday, Thursday, and Friday this week. Monday and Tuesday are fall break. So I will see you a week from Thursday. And we will pick back up here. What I want you to do is I want you to catch up all of your homework, since we're not going to have any homework other than this. Catch up all of your homework up through as much of this section as you can. Now, if the application problems give you problems, I will have my iPad and I will have my laptop with me. Click that Ask My Instructor button. If you've got questions on anything, I will only be at the hotel in the evenings for the rest of the week. So it may be in the evening before I get back to you, but I will answer you. Okay? Y'all enjoy your fall break. And if you want to drop by in Louisville and get your test, I will have them. I will leave them in the math office for those that want to go by and pick them up.
Chance to finish the technical skills check
Okay,
before
let me
I.
fix it for you. Actually, do you want to do the skills check? You want to do the, well, wait, let me look. 'Cause That might not be true for y'all. There's one of them where the skills check is actually harder than doing the homework for it. But it might not be yours. You did a lot better on your test.
Did I?
I haven't graded the last 3 yet, but you were doing really well up to that
I
point.
know there was like one question that I wasn't sure on, but I was pretty sure about just about every question.
Yeah, I saw a big improvement. Actually, let me just go to gradebook.
So we figured that out, fixed it, and I was chilling up there forever. Yeah.
And
Oh, you did the homework.
yeah, it was. I did that one, but it wouldn't let me do chapter 12.1 because I didn't.
Yeah,
finish
that's
that.
okay. Well, let me fix this. I'm gonna give you 90% for the quiz. That way you don't have to do it,
Okay, awesome.
since you've already done the homework. Let's see.
And so I should be able to do all the homework and stuff. No problem.
Yeah, no
All right.
problem.
All right, awesome.
Everything should
Thank
be
you.
fine.
Still down to do some homework.
Sure.
Cool.
That's cool.
You also have, my exam grade.
I do not have it completely graded. I told everybody at the beginning of class, I've got all but the last 4 graded, I think, but I should have them done in a little while,
Okay, cool.
because it doesn't take very long to grade them.
Okay.